here. Wait for it to go live.
I dropped the URL
For the YouTube video?
Yep.
How'd you do that? Anyway, I believe you. I believe you. Sounds good to me. Okay. This is our last lecture that's not you guys presenting, right? And we made a long list. Huh. It's not supposed to move like that. Somehow it unscrewed, and since it's all plugged in, it's going to be hard to re-screw it on. I can screw it up, but I can't screw it down. We made a long list of things we wanted to talk about this term. And then we pivoted like in week 3 or something, and we decided we actually spent the rest of the term sort of talking about CAM software and Esprit and programming in CAM software. So I have titled today's lecture, Everything Else We Want to Learn About Computer-Aided Manufacturing, but Forgot to Ask. And so I kind of want to review that list, and I think if I go to the syllabus schedule page, it has most of the stuff that we came up with wanting to do and the order we wanted to do it. And we kind of got hung up here and went back and forth between these two for most of the term. And I think that was what most of the people in the class wanted to do. I hope that worked out for us. And so we said we were going to talk about PLCs, so programmable logic controllers. We said we were going to talk about automation and robotics twice. I guess we didn't miss that much. Oh, that's because there was stuff I wanted to talk about that you guys didn't vote for the first week. That was why. So there's a few other things that I want to cover. Anybody know what a programmable logic controller is? You know what it is? What is it?
It's like an industrial computer that's programmed with ladder logic, and it uses sensors, actuates motors,
Yeah.
various factory automation.
Yeah. So mute, room control. Up. Yeah, so a PLC programmable logic controller. And you said and it's used for factory automation, right? So it tends to be used for and a single factory could have thousands of PLCs in it, or it could have a couple of PLCs in it, 1 or 2. But most CNC machine tools, for example, the XYZ motion and the probes and the inputs and outputs are actually driven by a PLC that's inside. Some of them have like a PC or something like that. The last time I knew, the Haas controllers ran Linux in their operating system on top of Linux, but there was a PLC driving all the motion, right? So there's a PLC at the back end, and you just don't see that interaction. But it's this logic, they call it ladder logic, the programming language for these. And it was, I actually got to meet the guy who invented the PLC. It's pretty cool. His son actually went to WPI a few years back, but he, the way he tells the story of inventing the PLCs, the guy's name is Dick Morley. And he was an electrical engineer. worked for a manufacturing company, and they made actually he worked for a company that sold automation systems to manufacturing companies. Sorry, and so every day he would go to work, and so what's a factory automation system have to do? Let's sort of think about what the tasks are in a factory automation system. So let's picture there's a lot of different automation systems that could happen, right? So they have automation systems that drive car manufacturing factories. One that you see often would be like a bottling plant. So if you've ever drunk a beverage out of a bottle or a can, it's been through a bottling plant, and those tend to be controlled by PLCs. And so think about the processes that have to happen here. So you can envision that you're an empty bottle that's going to get filled with. What should we fill the bottle with? We can choose. We're designing our factory. What do you guys want to fill the bottle with? Shaving cream? Whipped cream? Chocolate syrup? Oh, I do not want to work in that facility. Oh, yeah, it smells like chocolate all the time, which you get tired of eventually. And that stuff is sticky. Everything is going to be sticky. But okay, chocolate syrup. All right, so if we want to create chocolate syrup and fill bottles with it, so there's like squeezy bottles, what are the steps that have to happen? Yeah. So we have to move stuff. Right, so we have to move stuff from place to place. We actually have to create the chocolate syrup. Right, we're going to have chocolate syrup ingredients coming in. Water is going to be one of them, probably. Cacao powder, and I hope so. Maybe just artificial flavorings. Right, so we're going to take our water and our artificial flavorings, and those have to come in a metered way, right? So you have to measure. We may have to pump it from one place to another. So we have to measure how much we're pumping, and we mix them in there. And maybe they go into a vat, right? So they flow in there. And then maybe we have to have a mixer in here, a paddle that sort of spins around, and it gets mixed. And then we have to pump it out, right? So we have to make the chocolate syrup. And so we've got here pump on off. Right, we have to turn a pump on and off. We have to turn a pump on and off here, same thing. We have to measure flow on both of these, right? And so if you didn't have a PLC, you didn't have a system to do this, we could still control this, right? We could have a relay that controls the pump. And so a relay is just when it gets a signal, it turns on, gets another signal, it turns off, right? So it's a remotely controlled switch. We could have a relay that turns the pump on when somebody presses the start button, maybe. Start the pump. And then we have a sensor over here that's monitoring the flow. And when it measures the correct amount of flow, it can send a signal back to the relay to turn it off, right? So you can have it. So, I mean, it's sort of like, you could even do if certain simple things you might do with a mechanical system. But if you've ever flushed a toilet, the water comes back in, the arm lifts up, right? So there's different ways that you can accomplish that, right? So you can do that, do this, then you got to monitor whether or not the chocolate, it's probably going to add heat to here, right? Once it gets in here, you get to turn the heat on. So once the tank is at the correct level, so you get a sensor that goes your tank level. Once the tank is at the correct level, another relay turns the heat on. And then you do this, and then think about all the steps in the bottling, right? That's just to make the chocolate syrup. Then you gotta get the bottles to the right location. When the bottle's at the right location, you gotta fill it with the right amount of chocolate syrup. Once it's full with chocolate syrup, you gotta move it over, maybe check to see if it's full. Probably not all of them get full. Then you gotta put labels on them. You gotta put the lids on them. You gotta put them in a pallet. You gotta put them in the truck and send them to artificial flavorings. Probably not Whole Foods. Probably Whole Foods. We just call it organic.
Hey,
Artificial flavorings. Organic. Not made out of sand. Who is it that's eating all this inorganic food? Right? Doesn't most of our food have carbon in it? Doesn't that make it organic? All right, so we got all those things. To do this in the olden days, back in the 1960s, because they had bottling plants in the 60s, right? You could go buy your 6-pack of Schlitz beer back in the 60s, even before that. So they had these bottling plants forever. To do this, it would take miles and miles and hundreds of miles of wire going back and forth to electrical cabinets, out to the sensors, back to the electrical cabinet where there's the relays. And then you've got to figure out the logic of when this relay opens, this one has to close, and this one also has to open. And it's like spaghetti, right? You do all of this inside these cabinets. And so Dick Morley, New Year's morning, 1969, he was a little bit hungover. They did go out the night before, he says. And he was sitting at his kitchen table in the morning, dreading the fact that he had to go back to work tomorrow morning, because he was going to have to figure one of these systems out and go, all right, because you got to route the wires, right? It's all got to look pretty and all that. He's like, I wish there was an easier way. And then he thought for a minute, still a little bit hungover, maybe on a second cup of coffee. And he says, what if, because transistors were kind of a new thing back then, and what if we put a lot of little switches inside a box, and we had a bunch of inputs that could go to the switch and a bunch of outputs that could come out of it. Now, they couldn't run at very high power, right? But you could do all the switching in a box like this big. Well, maybe it was like this big back in the day. You could do all the switching in that little tiny box. And we still got to run wires back and forth to the sensors. We still got to have the sensors in the field, but we don't have to have row after row after row of relay cabinet full of these different relays that we're running wires back and forth between. And so he actually started up a company, made his first prototype, went out and sold it. It became a $10 billion industry based on being hungover on New Year's Day, 1969. Trying to decide, what could I do if I go back to work tomorrow? So that's sort of the foundation of it. This ladder logic, and you say, but why don't we just use a PC today, right? Because we can do the same kind of thing. So PLCs, and you can, right? You can put I/O cards in your PC. You can have an industrial PC that have all these I/O cards, and you can run Windows on it, and you can have this input output and do the math and decide when to control things. Has anybody ever had to reboot their PC or Mac? Even my MacBook Pro, which is supposed to not need to get rebooted, has to get rebooted. My iPhone, I had to reboot yesterday. Right? These things all have to get rebooted. So PLCs, if you screw up, sometimes you have to reboot them. But they tend to be extremely robust. And the operating system is really simple. And they use and you mentioned ladder logic, right? And so they use this system of reading inputs and outputs called ladder logic. And so let's just I'll diagram a simple system here for you. And I can, if somebody reminds me, I can send you guys an email. There's some really cool online PLC training. where you download an emulator, and so it emulates a PLC, and you can go through a bunch of canned steps to really learn how to develop ladder logic and to go through and program ones. There's somebody, or hey, remind me to send them a link. It's like $35 for the thing. You get to download the software, keep it forever, as long as you don't switch computers. But it's pretty good. So if somebody's interested in going further into developing ladder logic programming and stuff like that, I'll send you that resource. But so let's think. These PLCs to control streetlights, like walk, don't walk, drive, don't drive kind of streetlights. So PLCs control those little green boxes next to the thing. It's got a PLC inside it. Used to be a bunch of relays back in the old days. Now it's PLC. So what are we going to do? We got to do we want to sense if the car's coming? What are the inputs that we're going to have? We're going to, so 4 directions. Right? So we got a sensor here. What is this? North, west, east, south. So we got a sensor. So we're on the, probably put this one on the other side, that side, right? So we're in America. We have it on the right side of the road. Okay. Could have been in England. Who knows? So we've got 4 sensors that detect whether or not there's a car present. There's no crosswalk. Let's say there's no crosswalk, but you could do the same thing, right? You could have 4 more sensors that are really just a push button to sense whether or not somebody pushed the button, right? So, and we've got 4 directions of light here, right? And each one of these has 3 light bulbs in it. Yeah. Okay. So we've got north sensor, and so this would be like the north facing light, and north, red, yellow, green, and then you could do this for all of the things, right? So this is an output, or sorry, this is an input, and this is an output, right? So we're going to tell it to turn on the light. You could also have a sensor that checks whether or not you actually turned on the light. Very important in nuclear power plant control systems, for example. The accident at 3 Mile Island happened because their indicator in the control room told them the position of the switch, not the position of the valve. So they had told the valve to close, and the indicator said, yep, you told the valve to close. But it didn't actually monitor whether the valve was closed. That's why all the water ran out and bad stuff happens. So presumably we've got a driver that can decide whether or not the light's on. Okay, so you've got all these different inputs and outputs. And so what happens when you run one of these ladder logic programs in a PLC is the first thing that the system does is it checks, and so this could either be on or off. So it's all binary, right? It's a 1 or a 0. It's either 1 or 0 as you go through here. So what it does is it checks the status of all of the inputs and all the outputs and puts it in its memory registry. So it says, all right, so this sensor is on, this light is on, it remembers all those things. And then you've got a program that it steps through, and it's like you lay it out as a ladder. So the first thing you do is you check which sensors are active, right? So if this sensor is active, then you know that there's a car there. But you got to also say, if this sensor is active and that this light is green, then you don't do anything, right? Because the car can just drive through. If this sensor is active and this light is green and this sensor is active, you'd have a time delay, and then you'd make this one go yellow to red and this one go green, right? So you set up the logic of what you want it to do in the order that you want it to consider those different factors. It reads the status of all the things, then it steps through the logic. Then it reads the status of all those things, and it steps through the logic. And it reads the status of all those things, and it steps through the logic. And now we've got 50 microseconds. So it does that really, really fast. The order that you put things in your ladder diagram matters, but it's also important to know that it reads all the statuses and then it decides what to do. So you could have in your logic. So we said if the sensor's active and the light's green, do nothing. But if the sensor's active and the light's red, then you check the other sensors, maybe you see what's going on, you decide whether or not to do the time thing, and you set. So say this one was green, you set this one to red through the cycle, and once this one is red and the other status and the sensor is active, then this one turns green. So it'll check the status of this and decide what to do about this also. But it only does that. It only does the checking once at the very beginning. Ladder logic, very robust.
Very robust.
They
They
run
run really, really, really fast. Some of them have a Windows interface. Don't worry. It's running in a top layer that doesn't impact the operation of the PLC. Once you set them,
they go.
you don't have to keep your programming computer connected to them. They just run until they stop running.
Most of if you end up doing PLC programming or PLC maintenance in a factory, most of the time you're not debugging the program. When you create a new program, you got to figure out, does it work? Did I screw up making the program, right? Is my logic correct? Once it has successfully operated and it screws up, it's always because one of the sensors is broken. And then you have to figure out which sensor is broken and what's broken about it. We have a who's ever used mini mill number 2? Who's had it not probe in the right direction, right spot? Like it wants to come down probe the tool, but it's not lined up with the probe. It's the thing on mini mill number 2. It's because when it does that power restart, it drives over a limit switch to make sure it knows where the end of travel is on the table, and it drives over it and says, "Hey, that was the limit switch." Then it reverses direction and drives back over it really slowly, so it can say, "At this encoder point, that's where the limit switch actually trips," and that's how it sets that position. Yeah, so it drives over the limit switch, then slowly comes back, and that particular limit switch is a little bit slow to come back down.
So it would be kind of like how the 3D printers like level themselves.
Yeah, similar. 3D printer would do the same sort of thing for leveling because it wants to know exactly where that point is. But if that machine hasn't been on for a while, that limit switch responds slowly sometimes. And so then it's off in its count for where it is, right? And somebody tries to probe and it comes down the wrong place. And they say, I need to calibrate the probe. So you get the little probe calibration thing. They go through the process of calibrating the probe, and they calibrate the probe, and then they probe their thing. And then next time it drives over that limit switch, now the limit switch is warmed up and it just flops down correctly. And now it knows where it is, but we've calibrated the probe in the wrong position already. And then people calibrate the probe again. So especially if it's the morning and you get that problem, don't automatically calibrate the probe. Power restart a couple times. Usually that limit switch warms up and it works just fine. But and so it's not the program, it's not the sensor, it's not even the calibration. It's the sensor is not working right. Unfortunately, it's hard to get to. Otherwise, we take those out, fix them a lot. That's sort of PLCs in 15 minutes. What else is important to know about PLCs?
Are they
No, there's a bunch of different manufacturers now. A lot of what you do in a PLC, you could also do with like a Raspberry Pi or an Arduino. What you get with the PLC that you don't get with the Raspberry Pi or the Arduino is that redundancy and the
It's my daughter's school.
I know
they're not calling
to tell me she
fell
fell
off
off
the
the swing
set
set
and
and
got
got hurt.
They're calling to ask why the heck isn't she at school today? I'm pretty sure my wife said she was going to call, so I didn't. All right, yeah. So you could buy a PLC for $1,500 and buy a Raspberry Pi for $15. I guess I don't know how much they cost these days. $15 depends on what accessories you put on them. Your Raspberry Pi solution will probably work until it doesn't. Your PLC will continue to work once it works. So that's sort of the difference there. Then we talked about factory automation. We're going to use PLCs to do it. The next topic on our list was robotics and automation systems, right? So these automation systems will tend to be built with a PLC. The robot controller will tend to have a PLC inside it. All those things. So PLCs are integral to all this stuff. If we were, and since we've spent most of the time talking about CNC machining in this class, and programming CNC machining in this class, if we owned a CNC machining business and we wanted to automate our processes, what are the kind of things we might automate? What are the things that we would do if we owned a CNC shop and we wanted to automate? So machine tending. So parts in and out of machine. And by having a robot put parts in and out of a machine, that means we don't have to have a person doing it. What would be the benefit of not having a person doing it? Yeah.
You need really heavy materials or ones that you don't want to touch.
So we might do this with so heavy radioactive, right? So dangerous. Could be hot too, right? So different things. So we would benefit if we had really heavy stuff, dangerous stuff. What else? What else would be a good reason to use a robot for machine tending? Yeah.
You do it faster.
It might be faster. Speed's certainly a thing we would consider when we're deciding whether or not to do it. Yeah.
There's an element of human error you see over.
So it might be more repeatable.
Yeah.
Did I tell you about the time I created an automated measurement system for the golf club shaft manufacturer? Yeah. Company in Massachusetts makes golf club shafts. Turns out what gets a golf club shaft from, or the golf club itself, because they usually attach the head before they sell it. What gets the golf club from the rack at the store to the cash register is how it looks. How it visibly looks is a big factor in whether or not you decide to buy it. I mean, you like the brand and all that stuff, and maybe you swing it around and you like the way it feels. But if it doesn't look good, you're not going to buy it. And so the way they inspect this, typically things like that, is you look at them. If looking visually good is important to you, then you have somebody look at it and say, yeah, that's a good one. pretty normal visual inspection. Yeah, they hired a consultant or they hired a new guy. I don't remember exactly how they came up with the data point, but they started looking at failure rates, and they, for some reason, were able to correlate that failure rates skyrocketed the day after the Red Sox lost every time. Because it turns out his name was actually Joe in this case. Joe was a big Red Sox fan, and he was pissed off the day after they lost, and therefore nothing was good enough, and he would reject parts that on other days he would accept. It had nothing to do with the quality of the parts. It had everything to do with Joe being angry, right? And so we automated that system by having it's just a simple laser that shined on it in one direction, a sensor in another direction, right? So you see how much light scatters back to the sensor, and then you move it at a controlled rate across the thing, and you look at the variation in light scatter. It'll tell you about the scratches on the surface. So we made a simple automated thing, and then we calibrated it by using Joe on a good day. Joe said, yeah, these are good, and so we measure all the good ones. We measure all the bad ones, and then we could see what's the difference in the signal between the good ones and the bad ones. So as we left it, somebody still had to operate it, right? You put the thing over the golf club and move it across. It turns out it didn't matter how fast you moved it because we were sensing how fast you moved it. What mattered was the distance between the scratches. And so we were doing that. So we didn't actually eliminate the person, but we eliminated the eyes, right? And you could envision how you'd set that up, and you'd have a conveyor that moves the golf club past, or you'd have a robotic arm that moves the sensor across it, right? So there's different things. So we can get more repeatable. What else? Why else might we want to automate putting parts in and out of a machine? Yeah.
You don't have a big staff.
It eliminates person. So there's two ways to look at that. And the people that freak out about automation systems and robotics say, you can't fire all the people. They need good jobs too, right? We've all heard that argument, right? Here's what happens, though. It allows us to use the person in a more effective capacity. People typically don't lay off their staff when they build an automation system. They typically have their staff go do something more valuable for the company. So I'm not saying it never happens. Certainly people get laid off. But it's likely that if the company didn't automate that system, and maybe they laid off somebody because they automated that system, it's likely that the company was going to go out of business and everybody was going to lose their job because they needed to have that savings, right? So often we're not firing the person. We're simply giving them a better job to do. When we look at this speed thing, so the robot can be faster than a person. In my experience, the robot's not faster than a person in most of these parts in and out of machine tending applications. A person could do it faster, but you gain on the repeatability. And when you don't have a person there, you're not limited to that 8-hour shift. And so the fact that the robot loads the parts just a little bit slower doesn't impact you if you run the machine for a few more hours. And that's actually pretty common in large manufacturing, so large machining facilities where they use robots. So they use a lot of robots at the Haas factory. By the way, if you're ever in Oxnard, California, they offer public tours. Totally go on the tour. I've been on the public tour, and I've been on a slightly more in-depth tour being out there because of our association with Oz. But they have 1 million square feet of manufacturing space under roof. That doesn't count the stuff they do outside because it's Southern California. It doesn't rain that much. They actually do some of their manufacturing outside. It was a big earthquake shortly after they built that building, and roof caved in a part of the factory during the earthquake. Nobody got hurt, or I think it was, I don't know, nobody got hurt that I know And so all the other businesses where they had damage like that, they're waiting for their insurance checks. Nobody starts up again. They're waiting for their insurance checks to come in. At Hawes, they rented some backhoes, pulled the roof off the machine tools, cleaned up the machines, and got them running again because they had to ship parts. You can send us an insurance check if you want to, but we got to make deliveries to our customers. So they have robots moving parts in and out. There's a joke that so they sort of staff 1.5 shifts. So there's part of a night shift that's staffed, and I'm sure there's part of an overnight shift. The third shift is partially staffed also, but pretty much they run one shift and operate 3 shifts. So everybody's there during the day, set things up, get things running, troubleshoot things, set up new processes, and then the factory runs overnight. There's a joke that says in the factory of the future, there'll be 2 employees. There'll be a guard and a dog. The guard's job is to feed the dog. The dog's job is to make sure the guard doesn't touch any of the machines. Right, but it's never actually going to get that way. So we could do parts in and out of a machine. We could, if it's heavy, dangerous parts, they could be hot parts. I did a thing. It could be. It can increase speed in the sense that you're not limited. It's more like time division multiplexing, where you spread the time out a little bit. Sometimes the robot goes faster than the person. Sometimes it can more. So sometimes you have to sort of place it and sort of fiddle around to get it in the right place, where the robot can put it repeatedly back in the right spot. It's repeatable. You can free up that person to do a more important task. The other thing on speed is, who's ever loaded parts in a machine for longer than 1 or 2 parts? You have. How many? In a row? 16. So after like the second one, it was pretty boring. Yeah. What was the cycle time between parts?
It took like 5 minutes per part. So it was not terrible.
5 minutes. No, I think 5 minutes is one of the worst cycle times you can have. Right? Because you don't have time to do anything else. But you do have time to think about something else and maybe even start doing it. I was doing one, we were making some parts for some alumni event or something like that, right? So they want like 500 little widgets or something like that. And one of my employees said, yeah, we can make those. And then nobody was there that day, so I was stuck making them. That's fine. I don't often get to run the machine, so it's fun for me to get to do it sometimes. But the cycle time, I think, was 8 minutes, which was, and it was 3 machines. There was 3 machines involved. So you take a part from one machine, move it to another machine, move it to the third machine, and the process of sort of swapping all the parts took about 3 minutes. So in between each iteration, I had 5-minute wait. So what do? Read a book, watch a movie, try to work on your assignments for the next class, right? So it was long enough that I could walk back to my office and sit down for like 2 minutes, then my watch would vibrate. I'd get up and I'd go change parts. I'd go sit back down, and so that kind of cycle time is really horrible. If we'd had a robot, if I'd spent another 2 days, I actually could have probably automated that whole thing. But it would have taken 2-3 days to get sort of a partial automation system set up for that. But if I'd had a robot, even doing part of the process, it would have made my life easier. I might have been able to set it up so that we had like a multiple fixture in one of the machines where the cycle time now takes 25 minutes, in which case you could actually get something done. Right. So the repeatability, and sometimes this cycle times are so horrible for employees. We've had in our shop 15 spindles running with 3 employees before, and it's a little stressful. But 3 people, each person basically running 5 machines at once, and so you have to time the op, and it only works if the timing works right.
which basically you go touch this machine, you take a breath. You go touch this machine, you take a breath. You go touch this machine, you take a breath. And then actually the fifth machine, he was manually making something. But it was, so those kind of things, you can keep multiple machines running and not lose your mind. All right, so part loading, part handling in and out of the machine. What else could we automate? And when we say this, and so we think of a robot to do this, right? Like you when I say part handling machines, you're envisioning like a 6-axis robot that picks stuff up, puts it down, picks stuff up, puts it down. It doesn't have to be a 6-axis robot. There's somebody here from the you're in the chess group, right? No, you're in the chess group. That's right. I knew somebody was here in the chess group, right? So you guys use the bar feeder for one of your parts or two of your parts, maybe. And so with that bar feeder, it's still an automation system. You can stack up the bars on the back of the machine tool, and it loads them in place, and it makes the right number of parts. I was using the bar feeder in that round thing of 8-minute cycle time. So you don't have to be using a robot. You could build this dedicated automation setup to do things like that, and that often happens in loading parts. You take a thing from here, you put it in there. What else might we automate? Or have we seen automated in our lab? Yeah.
Polishing, deburring.
So polishing and deburring is the thing that we like to automate. And again, so it eliminates the person. It could be hazardous materials, all those different things, right? So basically, we like to automate things that are dirty, dull, and dangerous. Those are the 3 Ds of automation: dirty, dull, and dangerous. So people don't like to go in the dirty areas. They shouldn't go in the dangerous areas, and they screw up when they're boring. When the job's boring, it's easy to screw up. So polishing and deburring. The challenge with polishing and deburring in automation is that it's usually not the same part to part. So that's actually if you had a good system, if you thought you knew how to do polishing and deburring right now, you could probably get $500,000 from the National Science Foundation or somebody to develop that system and prove that it works. The Department of Defense, these things is when you walk into Washburn 108, on the left-hand side, there's a blue box. It's got a robot inside. You guys have seen that? Yeah, so that robot came to us from General Electric at one of their facilities. They had bought 2 robotic cells from a robotic integrator that said they were going to set up a cell to do polishing and deburring of a particular, I can't remember what the part was. It was a welded part. So they were going to deburr the welds or clean up the welds after the welding happened. And it's easy to automate the welding. You have robots do the welding all day long. It's almost impossible to automate the deburring of those parts and actually have it done the way you want it to do. They tried for a couple of years to set that machine up and have it work, and they finally gave up. And they said, "Hey, WPI, you guys want this robot? Here's a list of things that would be useful in our factory. If you can take this robot and figure out how to make it do one of those things, we'll take the other robot and we'll implement it in our factory." So that's why that robot's there, is because it's really hard to do polishing and deburring. Polishing and deburring was not one of the things they asked us to figure out. They'd already decided it was too hard to do. But that's the thing. There's a lot of research being done right now to figure out how to do that better. There's some people who've got some good ideas. So polishing and deburring, what else could we automate in a CNC machine shop? Painting. So a lot of parts need to get finished afterwards. So part handling, painting, polishing. What else? What else might we want to automate in a CNC machine shop? How about inspection? So if you had me in M1800, you know that inspection doesn't add value to the part. It only adds cost to the part. So if it only adds cost to this part, we don't want to spend as much time on it. We don't want to put as much resources into it. So inspection is a thing that we'd like to automate. What else could we automate?
Packaging. So parts, paint, polish, inspect, packaging. What else? CNC machine shop. What are we going to automate? Anything else? Yeah.
Machine checks, like it start up and cool down periods, it self checks to make sure that it's running properly.
Yeah. So that it might fall in sort of inspection, but it's really a special case of inspection, right? It's that
So
it's validation of the system, checking the machine. One thing that comes up in long processes is that sometimes the tool wear can be a factor on a single part. So usually you catch tool wear by measuring every 10th part or every 100th part or every 1,000th part, and you monitor how a dimension changes over time by checking, depending on how fast the tools wear out, things like that. There are some processes where you have like really hard materials, and so ceramics. So ceramics, you tend to do grinding processes on ceramics, and so you have a really hard thing and a moderately hard thing with really hard bits in it, right? And so you spin this around and you run it into the part, and it's like having a whole bunch of little cutting tools. Those are like the sand on sandpaper, the shiny bits on a grinding wheel, right? That you see. Those could be diamonds. They could be different other ceramics, things like that. Really hard stuff, right? So as you do that, the bond on a grinding wheel wears out faster than the hard stuff. And then slowly the ground bits wear out, and that grinding wheel changes diameter over time. And we've seen it. If you've ever used like a bench grinder or something like that, over time the wheel gets smaller. So if you're grinding ceramics, and often these ceramic parts have very tight tolerances, you're grinding this ceramic part, and the wheel's wearing out, the part's wearing out, right? The part's changing shape, and the wheel's also wearing out. It's hard to predict that wheel wear to say 2/10,000ths of an inch in position. And so what we did often when we were grinding the ceramic parts is cut until we think it's going to be pretty close. Then load the probe in the spindle, go measure the part with the probe, adjust the program, cut again, measure with the probe, adjust the program, cut again, measure with the probe. You can also use that probe to automate the initial setup. So we had a part, 24-hour cycle time on the part. The operator would put the piece sort of in the middle of the fixture. Press, no, I had auto door closer. Just press the start button. Door would close. The probe would come out, locate the part. The first process would go probe the part. Next process would go probe the part. And 24 hours later, you come back and you've got a good piece. Operator never has to check it. So that's the kind of inspection in process that you can do. When I said inspection here, I was more thinking before you put it in the packaging, you can put it in a little scanner system that checks, is this a good part? And those kind of systems also exist for that. So you can automate those things. I think we've missed an important one here. Anybody think what it is?
In chat.
What is it?
Stock handling / processing from Sam.
Yeah, so you could automate. So you got to have, you need a piece like this to go in the machine to make your part, but you buy the stock in a 12-foot long bar. So they have automated bandsaws where you just put it down and it actually spits out the pieces in the lengths that you need them. You could even automate loading that bandsaw like with our bar feeder and the lathe, so you'd have different size materials there. So incoming raw material handling, you can automate that too. Which I kind of group in that parts, but it's a different step up the ladder from that. What else can we automate? Something we had a lecture about in this class. So let's think about the economics of a machine shop. What do the customers want? What are the customers willing to pay for? Because any business wants to make a profit, right? So that means you need to
sell the stuff for more than it costs to make the stuff. So what are the customers willing to pay for in the machine shop? They're willing, yeah.
Probably wholesale style sales.
Well, what they're willing to pay for is they're willing to pay for parts that fulfill their needs, right? They're willing to pay for parts. So customer wants good parts, right? Before we've made a good part, the customer also kind of wants to know how much it's going to cost, right? So in order to get the order, we have to figure out how much it's going to cost, tell the customer it's going to cost that much, convince the customer that we can make the part. Those are before we've even gotten an order. Once they order from us, we've got to get stock material, move the stock material to the machine, put the stock material in the machine. We've got to program the stuff, right? We've got to set up the machine, program the stuff, put the tools in the machine, put the material in the machine, run the program, do our inspection, maybe do polishing and painting if we need to do that, right? So a whole bunch of stuff we need to do before we even get to making parts, painting them, polishing them, inspecting them, packaging them, shipping, right? Ship it to the customer. Customer wants good parts. They actually pay for receiving invoices. That's a step in the thing too, right? At the moment the shipping happens, you want the invoice to happen too. So what if you had a system where when the shipping clerk scans the package and calls UPS, it automatically sends the invoice? So you can automate a lot of those customer interaction steps. At the beginning, the customer needs good parts. That's what they need. But it's not the first thing they ask you for. First thing they ask you for is a price. They want to know how much. No, the longer it takes you to tell them the price, the more certain they are somebody else is going to make the parts, right? So if you take a long time to develop that cost and things, so it's easy, right? Customer says, how much to make this part? Say, $1 bazillion. Now, at least if they buy the part, I'm profitable because I know it's got to cost less than that, right? Right, so you can actually have systems to help automate the process of quoting the part and tracking the part through the process because the customer wants to know, am I going to get my parts on time, all those things, right? And so that is actually where a lot of the computer-aided manufacturing that happens in the world actually happens, is that customer interaction. You log into a portal, you check on the process of your parts, right? They do it for Domino's. Right? Domino's can tell you when your pizza's in the oven, right? So you could automate those kind of steps in your process because the customer also wants to know if their parts are in the machine shop. You take it off?
My group decided to meet now.
Okay. I guess
I have no idea.
I guess they didn't want to learn anything, or maybe they thought that there was no learning happening today. It's possible there's no learning happening today. So you can automate all of those different things. We and a robot is really just a specialized automation system, right? And here at WPI, we've got special rules for what allows us to call it a robot or not call it a robot. But what makes something a robot? Yeah. So it needs to have automated operation. What else? Anybody know? It needs to have sensors. It needs to have inputs and outputs. It needs to be reconfigurable. Oh, maybe that's not the WPI rule. It's totally the standard though. Or you need to be able to change it to go do a different task. So it needs to be programmable and reprogrammable. But it does, call it a robot. Don't call it a robot. Is a CNC machine a robot based on our definition? Can run unattended. It can be reprogrammable. It's got end effectors, right? CNC machine is a robot by this definition also. So
Anybody know where the word robot came from? Etymology. Really? Any robotics engineers? Like, sort of. You don't know where the word robot was first used?
I know how to say robot in language.
Me too.
That's it.
Me too. Me too. I can say it in Japanese.
Oh, I say Chinese.
Roboto. At least according to the song, right?
Is that where the word came from? The same song?
No, it's almost as good. It actually came from a Czechoslovakian playwright in the 40s, and he wrote a play about these autonomous people that would do work in factories and stuff like that, so people didn't actually have to work. So he invented the robot at that moment. He invented the word robot, and then it was picked up by science fiction writers, and then eventually science often follows science fiction. So eventually we started making robots. So the word robot isn't that special, except for people that like the word robot. But if you think about a robot, and so I think we're transitioning from what we can automate in a CNC machine shop. Right. Oh, the thing that you guys didn't say, which we did in the class, we talked about it in the class, was automate the programming part. Right? If you automate the programming part, and you can do that really well, you can actually use data from a program that you automated in order to generate that quote to give to the customer, and then actually know what the cost is. Okay, so let's think of robots in the broad definition, and I think the WPI definition is a pretty good one. So it is reconfigurable, it is autonomous, and it can be reprogrammed. I think that's sort of is reconfigurable, reprogrammed, and it's got sensors, it's got inputs and outputs. What is the objective of every robot that's ever been built? Every robot that's ever been built, ever been conceived of, has the same objective. Yeah. Say again?
Get to the end of the program.
Get to the end of the program. The objective of every lecture is to get to the bell, right? I just had visions in my mind of that stupid TV show Saved by the Bell now. The objective of every robot is to position and actuate an end effector. Right? At each step in a program of the robotics program is involved in positioning and actuating an end effector. So you can open it, you can close it, you can twist it, you can position it over here. But every robotic thing that happens is about positioning and actuating an end effector. Even a Roomba, right? A Roomba is, so what's the end effector on the Roomba? Is the little spinny things that pull the stuff up into the little container. And so it actuates by turning that on or not turning it on. I guess turning it off, right? And it positions by moving around. So because if that thing just turned on and stayed in one place, for a little while you'd have a clean spot, and then you have a hole in the carpet, right? So it has to move. It's not functioning correctly if it's not moving. The welding robot, right? So this is one of the early robotic applications that you saw on TV, right? Because it's kind of cool because welders make sparks, and so it makes very dramatic video of robotics. And so you get the car manufacturer, you get the car coming in on the little conveyor, and you get the welder going in, sparks everywhere and all that stuff, right? And so we like welding with robots because it eliminates that being next to the dangerous thing. It's repeatable, it can be consistent. We used to have a welding robot here at WPI. Came out of a General Motors factory with a TIG welder and the robotic arm and all the control systems that went with it. And when I needed, it was a MIG welder. Sorry. When I needed to weld something, it was easier for me to program the robot to weld it than it was to actually make a good bead by hand.
could make a good bead by hand, but the robot always made a good bead if you knew what angle to put it in there and how fast to move it, right? Always made a consistent bead. So when I would weld stuff back in the day, I would use the robot to weld it, even for a single weld. If I was a good welder, it would have been more efficient just to pick up the gun, do it. But it's all about positioning it, getting it the right orientation, and turning on the welder, turning off the welder when you get to the end. All those robotic steps are all about positioning, activating end effectors, regardless of the designer of the robot, all those things. That's the profound thoughts on robotics. What else do you guys want to talk about? We got what? 40 minutes? Yeah.
Maybe like robot programming, some of the different methods of it. You teach editing.
So each robot is going to be unique in the whole robot programming thing, but there's some common methods are you basically have the robot do it manually, right? And whether you're using a teach pendant that's maybe it's got a joystick on it, or you're pressing different buttons to tell it move this far, change this angle, move this joint, and with like a 6-axis robot, which is when we say industrial robot, that's what you visualize as a 6-axis robot with one of those arms that does this stuff, right? And so what are the 6 axes? So you got this axis, right? So that's 1. You've got this axis. That's 2, 3, 4, 5, 6. Right? So assuming I lost my left hand, could be a 2-armed robot, right? So that would have more axes. Let's put this one, right? So I could be a 6-axis robot. Right? And so I'm just laughing because it's a good thing I did my yoga this morning. Right? So this axis can only go this far, right? Pretty much it can only go this far. It runs into a hard stop. It's probably a soft stop over here, right? A software stop, so that it doesn't keep hitting that hard stop all the time, right? And this axis, oh shit. This axis could actually go further, but it runs into the robot. That's a problem, right? But it can only go that far in this direction. Likewise, this one, when I get shoulder flex, this is totally more than 6-axis robot standing in front of you, because I get more degrees of freedom. But each degree of freedom is sort of limited by something. And so one thing that can happen and so again, it's about positioning and actuating an end effector. And so if I need to pick up the pen and write on the whiteboard, that's our task, right? So command me. Right? First thing I'm going to do is face the pen, right? So I'm going to move axis 0, axis 1, right? And I could move this one down. I could maybe do this. That's actually, I added an extra axis there, but no problem, right? So I was sort of as close as I could be. I could do this. I could do this. I could do that. I can grab the pen, right? I'm stuck. Right? I can move up. I can move like this. Oh, the robot needs to be on a carriage. We need to add an axis. Right? And you can do that, right? If you're designing a robot, you can do that, right? And then I need to do all kinds of motions to do writing. This is a common thing in robotics classes to program a robot to write on a whiteboard. Hardly ever does anybody program the robot to then erase the whiteboard. Everybody gets all excited about writing on the whiteboard. They never erase the whiteboard. It's totally uncool to leave your stuff on the whiteboard, by the way. Right? So you can do those things. So what often happens is I know that, so when I'm here, I want to be over there. And so maybe I could move like this, right? And with a lot more yoga, maybe I could actually do it. I mean,
I suppose, right? If we had the carriage, I could write now. But it would have been better to have gone around like that to do the writing. And so you get into positions where you can't move from where you are to where you want to be without sort of unwinding. So that's a thing to look out for in robot programming, regardless of the method. It's pretty common to do it though, where you basically do what I just did. You sort of record a macro. You record the program of doing those things. Move to this point. Turn this joint. Actuate this actuator. Right. So you step through those things. We have now we have a new class of robot. We call it cobot. And so some special things about the cobots. So they say co because it could be we'd have a cobot here and a person here. Usually in robotics applications, once you press start on the robot, if a person walks into the space, there's got to be sensors that shut everything off as quickly as possible. Because the robots can move with speed. They have enough inertia to do work on your body. That's basically right. That's how you get hurt in any instances to do work on the body, right? Let's say you break a bone, enough force and distance to break the bone. You can have all the force you want as long as there's no distance, it won't break the bone. Right? As long as it doesn't move into you. Right. So in a cobot, they've got built-in intrinsic safety systems that it can't actually hurt you. Right? Even if you piss it off and it tries to punch you in the face, it can't develop enough energy to hit you. Sometimes they'll have sensors that if it touches something, it shuts down and all that stuff. But in reality, they just don't make them strong enough to hurt you. That's sort of the easiest way to make it a cobot. It just can't hurt somebody. And I think this not hurting your coworkers thing is kind of overrated. Because if you had two people on the assembly line, they could totally hurt each other, especially if you piss one of them off, right? And if they're working on this big, heavy assembly line, they're probably pretty beefy and strong too. But especially when the Red Sox lost. So one of the other cool features about cobots is they tend to be even easier to program because they're made out of lightweight materials, and you can actually sort of disable the joints and move them around by hand. So with a big heavy industrial robot, you can move it manually, but you're using a joystick and you're saying move this joint, move this thing, or move this endpoint. And you can get different frames of reference you can use. You can say, we'll define a coordinate system based on the way the tool is pointed right now. And then you can have it always stay in that coordinate system to move around. So you can do a lot of things like that with that manual teach pendant, or with programming without a teach pendant, just typing commands in to do those things. With the cobot, it's really nice because you can say, I want to release the shoulder joint, and I want to move it like this. And then, no, I want to release the elbow joint or the auxiliary shoulder joint and move it like that, things like that. So you can actually release all the joints at once, and you can sort of position each thing the way you want it to, and say, all right, here's the point I want you to be in. And then you say, all right, here's the point I want you to be in after that, and it'll figure out the path to go between them on the control system. So that's the other nice thing about these cobots, and tend to use them at CNC shops a lot for that part loading stuff for lightweight parts. And the reason for that is because they're easy to reconfigure. The problem, especially at a small CNC shop, the problem with getting a robot is you need a robotics engineer, right? You need somebody that's capable of doing all the teach pendant stuff and programming, reprogramming, stuff like that. And the vision of the shop owner, like the guy that has to decide whether or not to invest in this system, is if we hire an outside company to come in and program it for us,
when we've got a different part or we want to change something about how we make this part, we've got to hire that outside company to come in and program it for us again, or we've got to have somebody on staff that's capable of programming it. And the reason you see now cobots coming into those shops is because they're so easy to reprogram. We actually did a thing just before COVID started. Actually, COVID shut it down. We did a thing here at WPI where we brought in 7th graders and trained them how to use cobots to load CNC machine tools and write simple programs to do that stuff. So part of it was to get the 7th graders excited about STEM and engineering, all that stuff. But our other part of that was to show machine shop owners how easy it was to program a robot. Your 7th grader can do it, right? And so we never actually got to do that last part because COVID shut us down and we had to send all the kids home. And then the funding agency said, we can't wait 2 years. We were willing to wait 1 year, but you got to give us the money back because can't wait 2 years. So it's a thing. Did that help answer your question? Or, I mean, we could look at a specific robot and talk about the programming language for that specific robot, but that'd be down a rabbit hole and probably not valid for in the classroom. You have to be in front of the robot to do that. But each robot manufacturer has its own internal language for how the robot's programmed. They have their own software package for how you interact with that. But basically, it's point A, point B, what orientation, what do you want to do when you get there? And then how do you get from one place to the other? If you want to do a lot of math about the coordinate systems, like I mentioned, you can have different coordinate systems that you talk about. You talk about the joint coordinate system and moving this one and how that coordinate system moves, right? When I move this one, right? If you want to do a lot of linear algebra math to figure those kind of things out and learn to program, I think they're still using the ABB robot that's in Washburn in front of the lathe. ME 4815 or RBE 4815, same class, different course number. And you get to do a lot of linear algebra and figure out all the internal things. Never understood why they spend so much time on the linear algebra part of that class, unless you're designing robot controllers. If you're doing the designing of the robot controller, you need to do all that math and understand it. If you're doing using the robot controller, you need to understand that math exists and that there are points that you can't get to from here in certain orientations. But then you're going to want to learn how to use the software and program the robot, talk about robot tasks. But they switched me to this class instead of that one. I used to teach that one. What else? Anything else? If you want to do a research project on your own and learn about something that would be important, especially if you think you might be a manager at a manufacturing facility at some point or own a manufacturing facility at some point, learn about ERP software, enterprise resource positioning. I don't know. I know it's ERP. And what it does is it tracks those things like where is the stock material, where's the part in the process, and you can use those kind of tools so that you actually know what the operations is. That typically used in manufacturing facilities. It knows how many orders you have, where things are coming in, where things are coming out, tracks it through the thing. There's a bunch of different software packages out there. I've actually created one myself because I didn't want to pay any of these other companies to use one of theirs. I recommend using one of theirs. It's easier, probably cheaper than creating your own if you value your time. But yeah, anything else people are excited about? Want to learn more about, talk more about? What did we miss? We've said all the words that were on the schedule that we developed. But you want to do more robotic stuff. Yeah. We could set that up. You do some more robotic stuff in the lab. Doesn't either for credit you do like an IXP or not for credit, just come in and use the robot, figure something out. We definitely are gonna have to make more widgets for the alumni office coming up pretty soon. We do those for reunion weekend, and so if you wanted, you could figure out how to have that robot move the parts from the lathe to the mill. It's positioned where it is so that it can reach the lathe and the mill to do pretty much to make those alumni parts. Other parts like that. We make lots of widgets in the summer for people. The alumni office, the robotics program, stuff like that. So yeah, if you want to talk about that, and if you've got free time in your schedule, we can do an ISP. You can get credit for it, or if you just want to do it, or if we can find a budget, we can hire you to work on it, and you can learn while you're hired. Anybody else? I know you want to talk about mill-turn programming.
Not military.
What's that?
But not military.
Mill-turn.
Oh, yes.
A million the same setup. We'll go over machine and talk about that. I think it's the best way. Anybody else? Anything else? Anybody online? Nope. All right. See you guys on Thursday. Should we change the order of presentations on Thursday just to screw with everybody?
We could just do 5, 4, 3, 2, 1.
Yeah.
Oh, last off. 5, 4, 3, 2, 1. The last. Is anybody here from Group 5? Anybody here from Group 5? Perfect. 5, 4, 3, 2, 1.